LightNeuS, neural surface reconstruction in endoscopy using illumination decline. Colorectal cancer is the third most commonly diagnosed cancer, and it is the second cause of cancer death. Optical colonoscopy remains the gold standard for colonoscopy screening and the removal of lesions. However, we cannot yet reconstruct the dense 3D shape of large sections of the colon. This would enable exciting new developments, such as post-intervention diagnosis, measuring polyps, or evaluating the coverage of an exploration automatically. This is the problem we address here. Most endoscopes contain a single camera, so the natural way for 3D reconstruction is to use video sequences. However, occlusions, specularities, albedos, and lighting make it a challenging problem. To solve this, we rely on two key areas. First, in endoscopy, the light source is collocated with the camera, and it illuminates a dark scene. As a result, the intensity decreases with distance. In fact, it is a function of 1 over the square distance. This strong relation between light and depth was unexploited to date. On the other hand, endoluminal cavities, and in particular the human colon, are watertight surfaces. To account for this, we represent the colon surface with a sign distance function, SDF. The zero crossing always represents a continuous watertight surface. To do this, we built on the success of NeuS, a multi-view reconstruction method that uses neural implicit surfaces. Similar to neural radiance fields, they were designed for regular images taken around an object and sampling an hemisphere of possible viewing directions. In addition, it assumes static lighting, so the brightness in the surface is usually constant. But these two conditions do not hold in endoscopies. The camera is inside the colon, and this limits the viewing directions. Also, the light source is collocated with the camera and it is close to the surface, which results in a strong correlation between pixel brightness and distance to the camera. We model that correlation with this photometric model. The light source emits with certain radiance in this direction. Then, the emitted light attenuates with the square of the distance that it travels, from the source to the surface. This cosine term at the BRDF models how incoming light is reflected towards the direction of our camera. Finally, we also consider gain and gamma compression. The important term here is the inverse square distance that accounts for illumination decline. NeuS training sample points along the camera rays. However, the network is agnostic to the sample distance. In LightNeuS, we explicitly provide the distance of each one of these sample points, so the renderer can exploit the illumination decline. We also introduce a photometric model for the endoscope light and camera so that the inverse square law holds. With these two changes, the network can now estimate depth easier. Our results show that exploiting the illumination decline is key to unlocking the implicit neural reconstruction in endoscopy. It delivers accuracies in the range of 3 mm, while an original NeuS is 5 times less accurate or even fails to reconstruct any surface at all. In addition, we have observed that the watertight prior allows us to reconstruct areas that were not seen on the images. In this example, we see how the reconstruction on the right image contains the gray wall that was never seen in any camera. Our method has a great potential. We can use it to assess the quality of an endoscopy procedure. For example, after inspecting a colon section, our watertight surface displays visualized and non-visualized mucosa. The doctor can analyze non-visualized mucosa and make decisions about subsequent exploration. In the future, we can adapt our method for automatic report writing, or to guide endoscopies to areas that were not seen during the procedure. In the long term, we would like to get a full reconstruction of the human colon, and for that, we will use deformable models.